Section 14.7, catalysts. And a catalyst is something that's involved in a chemical reaction but is not used up. So it's not actually a reactant. You have exactly the same amount of catalyst at the beginning of a reaction and at the end. But if the catalysts weren't there, the reaction would happen much slower. So it speeds up a reaction, but is not used up in the reaction. So it's not actually one of the reactants. Okay, so normally it's a location that reactants are occurring on. So it might be, say, the surface of a metal, and that you've got a chemical, let's say a gas molecule or a liquid molecule that sticks to the surface of the metal, and that metal makes it very more likely for it to react. Okay, so so rather than trying to catch a cow, you put it through a fence and force the cow into a place you want it, and then you can cut off its horns or brand it or do some cruel thing to it. So in any case, it's allows it to happen more easily than it would have happened. Okay, and a catalyst, the reason why that it happens faster is not because it's an intermediate that's made somehow in it, because it appears at the beginning of the reaction. You have it at the beginning and you have it at the end, and you have the same amount at the beginning and the same amount at the end. What's actually happening is it changes the mechanism. The mechanism is easier, or it's a lower energy activation energy almost all the time. So let's look at this example. We've got a chemical reaction. Okay, it's an exothermic reaction. So we're going to have a certain amount of energy, a lower amount of energy. Here is the activation energy if there's no catalyst. Okay, so you have to have that much energy in order for the reaction to occur. If you don't have that much energy, the reaction won't occur, even though it's an exothermic. You're getting energy back. You're getting money back, but you still have to put this much of money into it in order to happen, and this is called your activation energy. If you have a single reaction with a high activation energy, it would probably act very slowly. You're not gonna have lots and lots of molecules with that amount of energy to spend on the reaction. But if you were to have a catalyst involved, in this case, I've got two humps. That means I've got two mechanisms. So that means here's one reaction. So this is the first step, and here's the second step. Okay, and then I come here. Well, this is cheaper. Okay, so if this is $100, this is only $75. There's more molecules with that amount of energy, so more are ready to react and more will react. So a catalyst lowers the activation energy, and by lowering the activation energy makes it cheaper for that reaction to occur. And since it's cheaper for it to occur, more of the molecules have the energy required to make a product, and so it happens faster. So here's an example of a metal. Okay, so I've got some hydrogen, and I've got some kind of a metal here, and I've got a hydrocarbon, and the hydrocarbon sticks to the metal, then allows it to basically uses it in order to form whatever molecule is going to be made. So since it happens, it sticks to it temporarily, then it assembles whatever's being made, and then it spits it out. It makes it much faster, but the same amount of metal is at the beginning and the end. The metal is not used up. It's just a location for a chemical reaction, and makes that chemical reaction easier and facilitates it and makes it easier, and so consequently it makes it faster. The last thing in this chapter is on enzymes. And an enzyme is a catalyst that's used in the human body. It's also, there's other, everything that's alive. There's all kinds of plant catalysts or enzymes and all kinds of stuff. But in the human body, almost everything is controlled by enzymes. Because, for instance, if I were to have a teaspoon of sugar and I set it on fire and I've got a flame, the amount of energy that I get out of that sugar by burning it is exactly the same amount of energy you're going to get when you eat a teaspoon of sugar, but you never get past your body temperature. You're never going to get, 2,000 degrees to burn sugar, but you're burning it at your body temperature. And the way it does it is the enzymes in your body, your digestive enzymes, the enzymes in your saliva, the enzymes in your stomach, the enzymes in your gallbladder and in your intestines, all of these things will make it easier or lower the activation energy to get the energy out, or to cause, say, sugar to turn into carbon dioxide and water, which is, breaking that sugar apart. But I don't have to do it at 3,000 degrees. I can do it at your body temperature. But an enzyme is a catalyst that reduces that and makes it happen. So I think the example of the picture, you've got some hydrogen peroxide, H2O2, which will turn into hydrogen plus water. Usually happens really slow. If you put something, they've ground up some beef liver and just a tiny bit of that beef liver, and it totally breaks it apart. It happens all the time in your body.